there are some questions, these will stay in the recording as well. I think that right now we have a couple of more students in the lobby waiting. One is named Prova, and I will not admit him, so I will deliberately. So basically, you should log in with your name and surname, so we keep the log of who is logged in or not. My suggestion is always to use your account, Politecnico di Milano account, otherwise it is not possible to admit you. Okay, now I see. Okay, I think that we are okay with the participant. I don't see any more participants in the lobby. Okay, which is good. Okay, so welcome back, everyone. Yesterday you had the first lab. Unfortunately, it could have been done in class, but it will be done in class in the next weeks. We had an issue at the very last minute. Good luck. We had the online fallback solution. The video of yesterday lab is not yet on the website because we have to post-process it because Francesco Lattari had some problem of connection, and we have two videos to put together, but it will likely on the website in the week. So what about today? Today, let me share my slides. So what I would like to do today is to talk about very important and practical issues of training neural network. What are these practical issues? Well, so far we have discussed the problem of what is a neural network, how to train it, backpropagation, and let's say these kind of issues. But we have not yet discussed in details the let's say practical things. So one of these is overfitting. So we have this nice model. We have the possibility to train these nice modules, and we need to just a second. I don't see why. Sorry, every time it is slightly different. Okay, just a second. Do you see me? Sorry. Oh, I see. Okay, sorry. Still, this tool is not yet fully under control. So let me share it again. So let me share it again. Okay. That's ridiculous. Okay. Oh, now I can share it. Okay. Okay. Now I see it. Okay. Sorry for this. Okay. So now I can see my slides and the chat and the presentation. So first of all, I would like you to mute, especially if you are Prova. The user which is connected as Prova should be thankful today, because the next time I will not admit you with a username like that. So all students should log in as their name and with their Politecnico di Milano account, not with a Prova account, which is I think not correct. Okay, so welcome back. Finally, we start today's lecture. it will be about training neural networks. So far we have seen let's say, the theory of neural networks, the background that is used to, let's say, understand what are neural networks. Today we will see into some practical issues that comes with training. And I would like to start immediately with the first one, which is probably one of the biggest issue with the neural network. And this dates back to the, let's say, universal approximation property of neural networks. As we know from theory, a single layer hidden neural network, single hidden layer straightforward neural network is able to approximate any nonlinear function. Now, this is good because it says that our neural network, if we give them enough layers and enough neurons, can learn anything. But it also comes with some issues. The first one is that we need to find the weights. So we need a learning procedure. This is faced with the gradient descent, backpropagation that we've seen so far. But it doesn't always converge to the solution we would like, and this has to be kept in mind. Second, it is true that they are universal approximator, but it might happen that to approximate a very highly nonlinear function, you need an exponential number of hidden neurons. So what happens is that the theorem says that in theory, a neural network can approximate everything, but in practice, this might become unnecessarily complex. And when it comes that a model becomes unnecessarily complex, what you need to face is the so-called overfitting problem. What does it mean? If you remember, during the first lecture, we discussed about machine learning, and we discussed about the different paradigms of machine learning. And deep learning is just another machine learning framework. And as any machine learning framework, it is aimed at developing learning models which generalize. What does it mean? It means that provide good results on new data. As soon as your model becomes overly complex, what happens is that you end up overfitting, that is, learning perfectly the training set, but then when you go on new data, your model is not able to provide a robust solution, so it will fail on new data. This is not a new thing, and in machine learning, this problem is called overfitting problem, and usually the solution which is proposed goes under the name of Occam razors, which says always prefer the simplest model you can. So the point is that neural networks are universal approximator. The tendency, you might be tempted to go as complex as possible, because then you will end up fitting any function or learning any possible classifier. But beware, because once you will see new data, there is a high chance that your classifier will not work as expected. And this is called overfitting. So overfitting is highly coupled with model complexity. So what does it mean? It means that, let me take the point. So it means that if you assume to have a set of data, these dots, coming from a quadratic model, which is the dashed line, and you don't know that this is a quadratic model, you might be tempted to use a very simple model, which is the line. You see that this line, that is a linear regressor, this line is very simple, too simple, and you get what is called underfitting. So you have a too simple model which tries to fit the data. In machine learning, using too simple models is also known as having high bias. So when you have a model with a high bias, it means that the model is too simple. On the other end, you might be tempted to use a neural network, a very, very powerful neural network. And what might happen is exactly what is depicted in the picture. What is depicted in the picture is that your neural network is able, which is the dashed line you see here, is able to basically fit all the data, which is pass through all the data points here. But you can imagine that as soon as you get another data point, for instance, let me use the pen here. For instance, if we get a data point here, which is pretty close to the dashed line, to the true model, you might end up having a very, very big error, which is, sorry, the one that is here in red. So basically, if you get a new point which is still close to the true model, but you have been fitting too much your data set, you see that you have a very low error on data that were in the training set, but very high error on data that are new. So the data on the training set like this are perfectly fit, while this one, which is reasonably close to the other points, is not properly fitted. So that's the so-called overfitting problem. That is, two complex models overfit the data and they do not generalize. So selecting the right complexity for the model is one of the typical steps in the process of machine learning. If you're doing machine learning, you know that you start from very simple models. Sometimes you even simplify those in case you want to do feature reduction or feature projection, or you make them complex and moving from linear to quadratic regression and possibly to kernel methods, and why not by using a neural network, because a neural network can fit anything. The problem of fitting anything is that you will overfit with a high probability. Actually, in general, if you don't do anything, it's almost guaranteed that you will overfit. It means that you will be very, very happy about the performance in the training set, but when you actually apply the model in practice, this model does not generalize. All the deep models, which are very famous and very, let's say, robust nowadays, have some form of generalization applied in order to reduce the gap of performances between training and test data. How do we measure if our model is working properly? How do we measure whether if our model is generalized? So first of all, we should not look at the training error. So the training error is not a good indicator on how good is your performance. Why? Because the estimate on the goodness of fit of the data of the model on the training data is always biased. Is biased toward an optimistic metric, because the new data will not be exactly the same. And if you perform a very complex model fitting on data, in principle, you could fit also random data. So you can fit random data if you overfit them severely. But this doesn't mean that you have a useful model. Let me make an example. So when you study for an exam, you have some exercises, and if you go to the exam, we never give you the same exact exercise that we gave it in class. Why? Because if that was the way of evaluating your preparation, you just study the exercise without not understanding any single word of that exercise, you will pass the exam, but it means that the exam was not meant to understand whether you have studied, sorry, whether you have understood or not. So what is usually done for testing a machine learning algorithm is to use a new dataset. This new dataset is called test set. So for sure, with Francesco, you have already seen this. Usually, what you do is to split the data into training and test. Training is the data you use for tuning the parameter and training the model. Testing is the set of data that you use to test on unseen example how good is your model. How do we do that? Well, there are different ways. One is that someone else will give you a new dataset. So you build the model in your lab or your home or your company, and then you provide to someone else the model. This someone else has a new data, tests the model on the new data. Sometimes there is not a second data set, or there is not a person who is, let's say, in charge of collecting new data and test your model. So one thing that you could do is to split the data yourself, hide some of them, and then use some of them for later evaluation. So this is called holdout set validation, and it's the usual way you do in class, or you do for the exam or for the homework. We take apart some data, we give you the training data, and then you test on the rest of the data. Another technique, if you don't want to hide the part of the data, maybe because you have only few of this data, is to perform a random subsampling. So instead of splitting, which will produce two independent sets, you can perform, let's say, a random subsampling with replacement. This creates a correlation between the training data and the test data. So you should take into account that if you do random sampling with replacement, you will end up with a biased estimate of your performance. Why this random subsampling with replacement is done? But this is done if you have small data set. If you have a small data set, you can, instead of removing 10-15% of the data point, you sample them randomly and you use them as a test set. Okay. Questions so far? Let's see if I have a question on the chat. Yes, I have some notes. Okay. Okay. Oh, I have a lot of questions. Let me go back and see. Okay. No, not the question. What is the overfitting definition? The definition of overfitting is training a model so to have a very low performance in the training set, which does not generalize on new data. So in a sense, you are overfitting when there is a big difference between training error and test error. That's overfitting definition. Can we ignore training error? Well, no, we cannot ignore training error. Training error is the error used by backpropagation. So training error is the error you use to tune the parameter. What you cannot do is to believe that the error on new data will be the same. How far will be from this is a matter of how much you are overfitting. What is k-fold cross-validation? Wait a minute. What is a subsampling? So a subsampling means to take a random sample. So you extract, let's assume you have a data set of 20 records. You extract randomly 10 of those, but you make a copy. So you copy 10 out of the 20. This is a 50% random subsampling with replacement. So in the last case, with random subsampling, we still have only one test set. It depends. You can repeat multiple time this random subsampling and average the result. But my suggestion is not to do this because it's a biased estimate. So you really need to do it if you have very, very, very small data set. What is k-fold? I will tell you in a minute. In the case the new dataset has a different distribution with respect to the dataset, can we still use it as a test set? Well, let's say that the test set should come from the same distribution of the training set. Otherwise, it doesn't make too much sense. So let me make an example. You have the problem of recognizing cars from motorbikes, from pictures, and then you get a data set where the hand sketch of a car. Well, this is a very different distribution. Even worse, you get a picture of a boat. So you have trained a classifier to recognize whether a picture is a car or a motorbike, and someone gives you the picture of a boat. Your classifier will give an answer, but the answer will be basically random because there is no correlation between the output label and the input. So the test set should come from the same distribution. Sometimes it happens that there is a small change in the distribution. This is called covariate shift or out of sample distribution, or there is a lot of name for the problem of test samples coming from a slightly different population. But this is not the case in this course. Is the last method equivalent to the bootstrap method? Yes, that's the formal name of the last method. What is the difference between validation and test? I will tell you later. Out of bag samples, correct? It is that. With subsampling, are we using the same data of the training? Yes. So we have the same problem about overfitting. Correct. It is a bias estimate. Regarding random subsampling for a neural network, what do we consider generally for a small data set in practice? So the bootstrap, which is the random subsampling, is done for a data set with less than 100 instances. I mean, if it has more than 100 instances, there are other ways to proceed. The split of the data will result in a model trained on less data. Are we introducing variance? Well, yes, but variance exists anyway. So the fact that you train on different data from the one you test, this is true. I mean, there's nothing you can do. Variance is an intrinsic property of the model on one side and on the size of the data set. So that's true. We are increasing variance, but not that much. I think that the real problem with the variance of the model is in the number of parameters, not in the number of records. What is the difference between subsampling and splitting? It's in bracket with replacement. That's the difference. If we split a pie, I have half of the pie and you have half of the pie. No one of us has the entire pie. But if you take a piece of pie and someone replace it, I will still have the entire pie and you will have a piece of pie. So basically, the key point is replacement. And this is a problem because this doubles some samples between the training set and the test set. So basically, do this bootstrap only if you have very, very, very little data set. And I hope that will not happen to you very often. So these were a lot of questions. Good, I'm happy. Let's move on with the slide and answer some of the questions that you made. And I just said I will this I will take later. First of all, one comment is that you should always have the same distribution, especially with classification. So if you want to do a proper evaluation of your model, what you should do is to preserve the distribution between the training data and the test data. In classification, this means that you should have the same distribution of classes in the training data and in the testing data, especially if they are unbalanced. So if you have a data set with a lot of instances from class 1 and a lot of instances from class and a few instances from class 0, I expect that also in the test set there should be a lot of classes, a lot of instances from class 1 and few instances of class 0. So it is very important to maintain the proportion of the data. This maintaining the proportion of the data is called stratified sampling. What does it mean? You first split the data of one class and then you split the data of the other class. So you maintain the proportion between the classes. Okay, now some of your colleagues have mentioned k-fold validation or k-fold cross-validation. Right now, we have discussed the idea of testing on one set. That means that let's assume we have a few set of records. So the bar here is the set of records. So let's assume you have n records. And let's assume you shuffle them. So this is equivalent to split it random. And then you take half of the data, which is the training set, and half for the test set. In the picture, they are half. Usually, you never use half. Usually, you use 10% of the data for testing, 10, 15 at most. You never use more than 20%, unless you have a very, very, very huge data sets so that you want to throw away some data. Usually you keep the holdout set to 10, 15%. Okay. The problem of this approach is that the performance will depend on how lucky you will have the split. So let's assume that there are examples which are very, very simple and they end up all in the training set. Examples which are very, very difficult and they all end up in the holdout set. This will be somehow biased. So it will be an unfair evaluation. So usually what you would like to do is to have a more fair evaluation. So in your exercises, you will always use this approach. So in all your exercises, you will take some test data out and you will trust that you have been lucky enough to split your data into equivalently difficult dataset. This is an assumption that you make and you trust this assumption. Now, the question is, what do we want? What can we do to make a more solid decision. Okay. Let's make the opportunity that let's make the case we have few data. If we have a lot of data, we just split into, I already said 50% of this picture is too big, but never mind. Right, let's make it 10%. But even if 10% is too much, we can imagine a different procedure to, let's say, validate your data. So one thing that you could do is to hide one sample, train on all the others, and compute the error on the hidden sample. Then you hide the second sample, you train a different model on all the others, and you test on the second sample. Then you hide the third sample, and you go on for n times. So this is more, let's say, it has some issues, but it's more correct as an estimate of your error on unseen data. Why it's more correct? First of all, because you use all the data, which would be the ideal case. Second, you test on all the data. So in the holdout set, you see that you train on some and you test on the other. And depending on how lucky you have been and how much uniform is the data, you might get a good estimate of your test error or a bad estimate of your test error. In this case, you use almost all the data and you test on all data. The problem is that with this procedure, you can do it only if you have a few data samples. Why? Because if you have few data sample, basically you repeat this training a few times. If n is too big, this procedure is impossible. So basically you have to do the holdout set, cross validation or holdout set validation. There is an intermediate procedure, and now I'm answering to the people that were asking me about k-fold validation, which is a trade-off between the holdout set, which is one data set out and the other in the training, which is the k-fold. K comes from the fact that you split the data in k independent groups. So in this case, we have split the data in 5 groups. And we repeat the training and testing procedure 5 times. So we train in the blue, test in the yellow, train in the blue, test in the yellow 5 times. You get 5 errors, k errors in general, and your small ek is the error on the holdout set, and then you average all the small ek to get the average error. In this case, you have trained at least once, actually 4 times on all the data. You have tested at least one on all the data, and usually this estimate is more accurate than the holdout set, the situation when you have only one test out, and the leave one out cross validation. So the ideal solution for testing a model, for selecting a model, is to perform k-fold cross validation. Second best option to select a model is to perform holdout set validation. Okay. I see there are some questions. Let me read them and answer to them. So if I understood correctly, we use cross-validation when we don't have a test set. Well, wait a minute. If with test set you mean holdout, the answer is no. If with test set you mean, let's go back, the new dataset, the answer is yes. So cross-validation is split the data and hide some of them for later evaluation. If someone provides new dataset, is your only solution. Let's make an example. So let's assume I want to build a model to predict if students will pass my exam given some features. I collect the data of all my students, I build this model, then I give it to a colleague of mine, and he will test on his data. In this case, we have the new data set. If I want to evaluate myself, the model, I split my data in k-folds and I do k-fold cross-validation. And in this case, I don't need the students of my colleague. Okay. Lots of questions. Okay. Okay, wait a second. Does the cross let me, sorry, there are, does the cross in cross validation stands for train test? No, the cross stands for you use the same data for the training and validation. Yes, maybe could be what you mean, but the cross validation means that you validate your data with the original dataset. You don't use an external validation set. But since you validate your model on the data that you have, you don't have to use the data you validate for training. So you split training and test. Okay, question. So in a k-fold with k equal to 5, we have 5 epochs in our training process. No, wait a minute. No. It means that every line is, every row of these is a different model that you train. It doesn't have to do for how many epochs you will train it. So let's assume I want to build a network to predict the cost of rice tomorrow, and I have a data set of rice. I train my model on the entire data set for 1,000 epochs. Then I have this model and I say, okay, this is the price of the price of tomorrow's rice. How good is it? I have no idea. I go to my friend and I say, can you give me a little bit of data more so I understand whether my model is good or not? And they say, no. Okay, now I have a model which is useless because I have no clue whether the model is good or bad. So I go back home and I split my data in 5. I take 1/5, I hide it, I train my model on 4/5 for 1,000 epochs again. So the model that I get, I can test on 1/5. I do this 5 times and I average. And now I know how good is my model and how much I should bet on my model or not. Let's go on. Are there some theoretical results to find the best k number of groups to split? Well, results are there in the sense that you can understand the variance of this estimator. This is an estimator. so you can estimate the variance. The problem is more a practical thing. The bigger is the K, the bigger is the number of experiments. So in practice, you never keep these two. Usually it's a 5, 10. But it's not because of the theoretical bound, it's because of the computational power. Think that every single row means to train a network. So if to train your network, it takes 1 day, if you want to do tenfold cross validation, it takes 4 days. That's why in your, let's say, homework, you will usually go for a more holdout set, not for a k-fold cross validation. But the k-fold is a better way to evaluate a model. K-fold is a biased estimator. No, why it is a biased estimator? Where does the bias come from? You have independent sets. So each time this is unbiased, and this is the average of unbiased estimator. I don't know why cross-validation should be biased. What do you mean by bias? Okay. If I use the same data 5 times for the training, does not increase the overfitting? No way. These are 5 different training procedures. So you don't use 5 times the same data. And using 5 times the same data, it's just a training mode. So don't stay exactly to what I said. Don't make some leap. Does cross-validation include also stratified sampling? It's up to you. When you split, you have to split stratified. So you have to consider this stratified. So after training our model with different combination test sets, training set, we will get different models each time. If the overall error is satisfactory, which model do we choose for future application? And indeed, you predicted correctly what was the next step. What do I do with all these models? In practical applications, there are two options. The first one is you keep them all and you average them. This builds an ensemble method. This is called bagging. And as a matter of fact, by averaging the output of this model, you get, in general, a better generalization performance. Another option is that why did you do all this stuff? Sometimes you did all this evaluation to understand how many neurons to put, how many epochs to train, and indeed, many often what you do is you use this cross-validation procedure to evaluate different models. At the end of the procedure, you have decided that the best model to use for this application is a neural network with one hidden layer and 10 neurons. At this point, you put all the data together and you train again this model from scratch. This is not an option that I suggest with the neural networks. The reason it will come later on, but you can do it, but you can do it under some hypotheses, and I will tell you later on which are the hypotheses. In which sense k-fold is better than leave one out? So it can be better than leave one out because the fact that sometimes dataset have let's say doubled instances. So leave one out might be sometimes might be tricked by the fact that you have a double data set. So if you have copies of the same data point in the data set, exact copies, in a sense, what happens is that you have you don't have total independence between the data set. So if you want to think in terms of theory, yes, leave one out, averages less samples. So basically it's, sorry, averages more samples. As a, let's say, theoretical convergence is less unbiased than k-fold cross-validation. The problem is, first, it is unpractical, and this is what I already said. Sometimes, if you have doubled data points, it might get to tricky results. So, and another thing that I suggest is not to do it blindly. So there are cases where if you want to perform a proper evaluation, leave one out is not the right thing to do. So for instance, if you want to do time series, if you have a time series, the right thing to do is to leave the tail of the data and not to sample in the middle. So there are situations where you cannot just leave one out, but you have to think a little bit what is the right thing to do. But the main reason not to do leave one out is because basically with big data set is simply unpractical. Okay. So in cross-validation, we don't split anymore the data set in training set and test set, but in training set and validation set. Wait a minute. I've never talked about training, validation, and test. This terminology is confusing, and it is very, very important now that you care attention. So here in this slide, I hope there is never the word validation set. I want to read it carefully with you. There is never the word validation set. This is a problem of terminology. This is validation, which is the procedure of assessing in an unbiased way the quality of a model. There is cross-validation, which is a technique which improves on leave one out and leave with respect to outset when performing validation. There is no such a term as validation set. I always say something about training set and test set, but not yet about validation. Here it is. Sorry. I apologize for that. Okay. So the term validation, and this is a critical issue, but it will come clear in half an hour. So the problem is that when we assess, the reason why there is an error is because this picture is taken from book, not mine. So validation is the evaluation of the quality of a model. And you do it by splitting in training set and test set. So the fact that you use k-fold cross-validation, it means that the test sets are 1, 2, 3, 4, 5. So that's the idea of k-fold cross-validation. So the idea is, no, we still have data set and test set and training set. The only problem is that we have 5 test set and we use it to validate 5 times 5 model, and that's the point. So let me finish to read the question. I don't get the difference between validation set and test set. So far, we didn't discuss about this, I'm sorry, here there is a written validation set, there should be written test set, but so far we only have two sets. One set is used for training, one test is used for testing. The training is used to fix the parameters. Another set is used to assess how good is the model. This is the important part. But in the end, we create the real model with all the data, right? Not necessarily. There is one case where the answer is no. So wait a minute, I will tell you later. Other question? Okay, so let me recap because I thought this was overly simple as a concept. The fact that I have so many questions, it means that it is overly important. To be honest, not doing the things that are written in these slides properly in a machine learning or data mining or data analysis process is probably the worst ever error. If you see all the papers or all the thesis defenses on machine learning, the first question that is asked to the student or to the researcher is how they have performed validation, and this is a critical step. Can you repeat the issue about cross-validation? It was something about the distribution of the sample in the validation set. I said some issues not with the validation, cross-validation, but with the resampling. If you do resampling, that might be an issue with the replacement. That might be an issue because you repeat the samples. So there is not an issue with cross-validation in general. The only issue with cross-validation is that you have to repeat 5 times or k times the same process. At the end, you have a better estimate than with the old out set, but you have to perform this 5 times. Another issue, if possible, with cross-validation is that you have 5 models to decide upon. What to do with these 5 models? Well, the first approach is to average them and generate an ensemble. Another approach will come in a minute. So right now, what is very important, and this was a key part, so that's why I took it aside. This is not related to neural network, and this is very, 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 very important. This is related to machine learning in general. Never, ever use the result on the training set as the validation or the measurement of the performance of a model. This is always true in machine learning. You need to validate. Validation means say if a model is good on new data. 3 strategies. First, ask for new data. This makes life very, very, very easy. Second, perform a holdout set validation. If someone will not give you new data, and you know, take the data out yourself. And then evaluate at the very end, when you have finished, you will never touch the model again. You will evaluate that model on the holdout set. You might say that the holdout set is too biased. It means that it depends on how lucky you are when you sample that. Okay, let's do it differently. Let's split it in K and let's do K-fold cross-validation. You try 5 times to get an holdout set, and you try 5 times to train the model, and based on the average, you assess how good it is. So this is the key part of this first hour, which is a key point. I mean, this is a key point. It is very a key point. I mean, this makes the difference between someone that knows what is doing in machine learning and someone that doesn't know what is doing. I mean, it's probably the most gross error ever to not use a test set for, let's say, assessing how good is a model. Please, I'm saying assessing how good is a model. That's the key word. Validation is a procedure to evaluate the quality of a model by splitting, sorry, too fast, the dataset into training and test for testing. Okay. The quality, yes. The quality will be evaluated on the result obtained on the test set. Correct. What do we mean by averaging the models after K4 cross-validation? Easy. In a classification, let's assume you have 5 models. Each of them will tell a class, and at the end you take the majority vote. Let's assume we are in a regression case. Each of them will give you an output, and you take the average of the output. So this is model averaging when you have several models. Okay. So if unfortunately my cross-validation test, there are samples similar among them, I don't validate with high accuracy or not. In a sense, this is always true. I mean, in a data set, they come from a distribution and they all come from the same distribution. There would be similar anyway. The problem with leave one out was more identical one. There will be always some, let's say, uncertainty on your evaluation. But we are dealing with big data, big problem, non-linear problems. So the subtleties of evaluation, I mean, we accept as they are. Indeed, as we will see later on, it is very complex to do a full k-fold cross-validation in the deep learning era. Because, as I said, if to train a model it takes 2 days to perform tenfold cross-validation, it will take a month. So, I mean, it really depends on the time you have. So that's why I'm making example with very small k-folds, because those have a cost. In the first case, enough data. Is a single validation run with the holdout set sufficient? Well, it is not a matter of sufficient. The answer is yes, it is. But the problem is, what does it mean by sufficient? So it will be obviously better than just trusting the training set. So never trust the training set error. I mean, you can have a 100% accuracy on the test never trust the training set error. So you can have a 100% accuracy on the training set and 50% on the validation or on the test. This is really possible. So do it with the holdout set. You can trust it. It is sufficient. It depends on how big is the data. If the data is big enough, it is clearly sufficient. But why testing on only one value in the leave one out? Well, if you have 10 sample, you perform 10 run, 9 to train, 1 to test. You have tested all the samples using all the remaining one. With small samples is the best thing to do. With big samples, so big data set, it's impossible to do. Okay. Yes, we can use averaging for regression problem, just average the output. How many samples? Don't ask me a number. I mean, all the theorems on the number of samples make assumption on the data distribution, on the data. In this case, I want to be really practical. I mean, we don't know the true distribution of the data. We will, in all our example, when I will give you pictures, we have no clue about the real distribution of the data, the variability of the data. I mean, enough data nowadays, if you think about text or about images, are millions of samples. Indeed, as we see the first day, the deep models started to work when we reached the million sample case or thousand sample case. So when you have, let's say, thousands of samples, I mean, there's enough. Nowadays, with neural network, hundreds, they are a few. So you have to take proper countermeasures when you are in the hundreds. If you are in the thousands or tens of thousands, things start to be better. If you are in millions, good. You are in a good shape, but then you have other problems. Okay, so I hope everything is clear so far. Train, test. Never trust the train error. Use the test error. Okay. Question. How do I apply this with neural networks? Well, obviously, I train a neural network on some data and I test on other data. If the two differ, I'm overfitting. So, test train on some data, test on other. If the two differ, I am overfit. Unfortunately, this doesn't help in reducing or solving the overfitting. This does not tell you what you should do on the model to reduce this difference. So, for instance, you train a model with 1,000 neurons, you test, and you see that there is a huge gap between the training data and the test data. If I do something on the model and this gap reduces, it means that this something was useful. But the fact that I measure this gap is not per se a technique to improve the model. It's only measuring the amount of overfitting, but is very, very, very important. Based on this measurement, we have a very important technique for reducing overfitting. And this technique is the first of three techniques that I will discuss today. So today, once that I have introduced the problem of overfitting, which is a discrepancy in performances between the training data and the new data that you will use, and once that I have said how to measure this discrepancy, that is, train on some data and test on new data, we can talk on techniques which can be used in neural network to prevent overfit. The most simple one, it's called early stopping. Just a second. Okay, what is early stopping? Okay, so let's assume we train on some data. we train on the data, and what we expect on the training data is that, especially when the model is very big, is that this training set error will go to zero. The theorem of universal approximator says that this error, if the model is big enough, goes to zero. The problem is that at some point here, if my training error goes to zero, I have performed overfitting. Now, I need a way to stop the training so that when I have finished, I have frozen my model, I have sent it to the production, the difference between what I get in the lab and what they get in production is minimal. For sure, if I send my model at this point, the model in production will not be optimal, because if the training set error is zero, either the problem is very, 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 very small, very, very, very simple, or we are doing overfit. So at some point during this trajectory, my model has lost generalization capabilities. So to better understand this technique, which is, first of all, my favorite, I must admit. Second, it is probably the easiest one. Let's figure this picture. Training error is the one we have at the end of the training. Then we froze the model and we send it to the production. Someone else will test in production the model and will pay us depending on how good is the model is in production. The very big problem is that if we send the model here and it doesn't work in production, we get fired. So training is what we get in our lab. Test is what they get in production. If the test in production doesn't go good, we are fired. Under this model, every one of us will probably test on itself the model before sending it to the production. So, training, the one you are minimizing. Testing is what the production will do to decide whether they will pay you or not. Here it comes, the famous validation. So the validation is a model, a data set that you use during the training procedure to validate what you are doing. So it is very, very important. This is very, very, very important. And people get confused on that. And I'm sorry if they get confused. But the problem is that in the literature, these are the names. Training is the data you use to minimize the error. Validation set is the data you use to understand if this training is overfitting. Testing is the final evaluation of the model done by someone else. So at this point, we can go back to some of the questions in the chat. So someone of you was asking what is validation? Is validation the same of testing? Because we call the technique cross-validation, they become validation instead of testing. This is generating a lot of confusion, I know, but this is related to the, let's say, terminology which is used in the field. So, training the data you use to minimize the error of your model. Validation is the data you use while training to check if what you're doing is correct. Testing is the data that you will use for the final assessment of the model. What does it mean? It means that by looking at the validation set error, you can take decisions. But when you have seen the testing error, that's finished. You will never touch the model anymore. So this is a very important step, because if you see this plot, so you're training, so on a training set, you are minimizing the error function. At the same time, you have an holdout set. And this holdout set is some data that you have hidden, and you decide to stop. Sorry, and you see that at this iteration here, what happens is that you get the minimum of the gap between your training and your validation. Then you decide to stop the training here, and this is the model that you will send to production to test. At that point, you will be paid by the result of the test. So these are the three data sets. The training is the one you will use to optimize the model parameter. The validation will be a data set that you use to make decision on this training. The test is the set that you will use to validate finally your model, and that's what the model will get under practical use. Okay, let's see. So many questions. I'm so happy. So happy. I mean, I'm really happy you have so many questions. It makes life so difficult to me, but okay, but it means that you are first keeping track of the lecture. Second, you are curious about this. Okay, let's see the question. Okay, I'm trying to figure out what is the last untold question. Okay, I'm over there. Okay. So, does the validation error in the picture increase because of the loss of generalization? Correct. Perfect. Is at some point, more likely here, your model is trying to fit all the dots, because, as you know, the perfect model is the one that passes through all the dots. At this point, you are not anymore fitting the parabola. What you're doing is fitting the dots. Something along the lines of the network getting too used to training data? Yes. In a sense, training, overfitting the training set is about fitting the dots, which is about memorizing the training data, which means losing generalization. Can validation set and training set coincide? No, no, because to understand how good will be your training model when not observing data, you need the new data, new fresh data. So you need another split of data, which will be different from the test. Why? Because you are allowed to take decision on the validation set. So in a sense, you will customize your model to stop at this point here, but it is not necessarily the best for the testing. But you don't know the testing. You never know the testing. Okay. Oh, yeah, that's a very good statement. So, training and validation set are in the preparation of the model, and the test set in the actual use of the model in some practical context. Correct. Sometimes you don't have the final use, you simulate this final use with the test set. Correct. Ideally, training, holdout, and validation should be disjunct pair. Uh, yes, instead of saying holdout, let's call it test. So training, test, and validation should be disjunct test. Training, you adapt the parameters of the model. Validation, you take decision on the training. At this point, the model is selected. You send the model at a different place, they test. Training, validation, test. Now, first question before you ask, where does the k-fold cross-validation comes in? At all levels. So what does it mean? It means that you can do a k-fold approach at all levels. So you can, for instance, split in 5, and you train, validate, and you test. Then you train, validate, and you test on a different split. Train, validate, and you test on the third split. And this gives you the average performance of your training model building test. You see that this is very cumbersome, so you will take a lot of time. So usually what you do, you take only one test set out, and you have a single holdout test set aside. But in principle, you could apply k-fold also in this case. Okay, I like this point. To sum up, we use a validation set to find where, when, stop our training. Aren't? Correct. This is the idea of early stopping. So early stopping is one approach. This is early stopping, is one approach that uses the validation step to stop validation set to stop the training earlier with respect to the minimum of the training set. At this point, you are done. So, in the first 7 slides, we have seen how to compute this validation set error. Am I right? No, in the sense, the first 7 slides, they will be valid for the entire your life in machine learning, independently from this early stopping slide. Based on the knowledge of those 7 slides, which says never ever assess the quality of a model on the training set, use another set, people have invented this technique, which says, well, if I have to use another data set to evaluate my data, I will use this data set to stop earlier. But this validation set is not the test set is another set. I hope this clarifies things. Based on what is written in the slide, then you should perform cross-validation at each, and then testing for a given, epoch, and then evaluate validate. Wait a second. Words are very important. So in this slide, we talk about validation set, not cross-validation. So what is written here is that at each epoch we perform validation, not testing. There is no test set error in this slide. So at each epoch we perform validation, and we stop when we decide that the validation has reached the minimum. Then we sell the model. Someone else will perform the test. So intentionally, I did not put the test here because the testing of a model is outside the procedure of building the model. And because it is outside, you will never come back. And if you come back, your procedure will be biased. Because if you come back, it is not anymore an independent test. You have conditioned your training on the result. And this is something you should never do. I don't understand why we use epoch to feed neural network. Isn't using many times the same data problem? Does it increase risk of overfitting? Epochs are mandatory because you are doing a gradient descent. You will never be able to perform training error minimization in one step. So epochs are mandatory. I mean, you have to perform many epochs to reduce the training set error. How can we know when we have reached the global minimum of the validation set error? Well, what you do, you monitor this for a longer time with respect to the minimum. So what happens in this case is that after a while, you see that the training set error goes down and the validation error won't go down. Now, in principles, you could go on forever, but you set the cap on, I don't know, 1,000 epochs. In practice, you don't want to do these 1,000 training epochs and then realize that you should have stopped after 100 and then you go back. So what is done in practice, it is to put some rules like if the validation set error does not decrease for 10, 20 epochs, I will stop and I will return the minimum of the validation set. The more the number of iterations, the more complex the model is? No. The more iteration, the more step of gradient descent you will be doing. So why not while using k-fold? Okay. So why not while using k-fold cross-validation put aside more weight for the output of the model which showed less errors? Yeah. Okay. This is again here in the slide. I'm not talking about k-fold. I'm not talking about k-fold here. There is no k-fold, such a thing like k-fold. In this case, I'm talking about the holdout set. So this validation is not k-fold. If you want to do k-fold cross-validation on the test error, we have to do k times this procedure. Now, Okay, sorry, I probably didn't understand your question. Uh, why not, while using k-fold cross-validation, put aside more weight for the output of the model? Okay, now I understand. Sorry. So the question is, instead of averaging, why don't we weight by we give more importance to models which had uh, a lower validation set error? Yes, you can. Correct. Okay. I don't understand the concept on k-fold on the test set. The k-fold averages the performance of the errors on k-sets, so to validate the model. The test set should be separate. Uh, Again, that's I know it's so fundamental, this lecture, that people get mad. Don't think about neural networks right now. Think about test. Think about you're doing a linear regression. So the most stupid model ever. And think the concept of k-fold on test set as you take the first fifth, you do linear regression, and you evaluate your linear regression. One error. You take another fifth, and you evaluate your linear regression. Second error. You take a fourth fifth, and so on and so forth. So you have 5 errors which you get from fitting your linear regression on 5 datasets. Now you have 5 linear regressions and an estimate of this linear regression on 5 different datasets. So you know on average how this linear regression performs on new data. This is evaluate. The test set should be separate. Okay, the test set is separate. Now, look inside the blue part, and each blue part is implemented this way. This way is how you implement the blue part. That is, inside the blue part, you take some data out and you stop the training based on the validation set on that data. Okay. What about reaching a local minimum, not the global? Okay, when you have a model which can fit everything, by definition, the global error is the overfitting. So if you minimize the training error set here, by definition, the global minimum is here at the end. That's the point where the error is minimum. The problem with neural networks is that they have one global minimum on the training set, which is surely overfitting. So I'm not so worried about the global minimum, provided that this local minimum is good. So here it is the problem of working with such a complex model like neural network. Is it guaranteed that the validation set has always a unique global minimum? Not at all. If you start from different random initialization, this plot will look different first. Plus, in this picture, I show it very nice, but when you see it in practice, it is way, way, way more noisy. So this is why usually you don't look for a minimum, global minimum. What you do, you say, okay, if will not improve for 10 epochs, I will stop. That's why you usually use this heuristic choice. So can you produce for the next slide the precise definition for training, validation, and test set and their use? Yes, I hope this will help, but I don't want you to use the. We'll see next slide that I will not want you to stick to my validation, my definition. Why? Because then you will go and work, and they will ask you to validate your model. Now the question is, what are they asking you? They will ask, with this sentence, more likely to test your model on a different data set with respect to the one that you trained upon. You can either call it as a validation test and a set, but in the literature of neural network, this is a different thing. Validation set is this picture. Usually in the literature of neural network, it is called test set. But I will come back to this definition later on. Why we say that we validate each epoch? The overfitting of a model depends only on the complexity, doesn't? Or it depends also on the number of epochs. In practice, it depends also on how much you train this model, in a sense that this technique, which is cross validation, is used to prevent overfitting by not letting the model fit all the training data. So the idea of early stopping is that while you learn your model, you first fit the, let's say, general model. So you fit the part which does not depend on the noise, which is not different between training and testing. And because of this, you will stop earlier. Epochs are needed to set up the weights and are used for each training set generated by the k-fold example, right? In practice, how does a split the data in this data set? I mean percentages. Usually you keep, this is really depends on the size of the data. Usually you keep 10-15% for the testing, 10 to 20% for the training, for the validation, sorry, and then 60 to 70, 80% for the training. So the big part goes to the training. So one example is 80, 10, 10. Another example could be 70, 20, 10, which are training, validation, test. Another example could be 70, 15, 15. These are reasonable questions. So training set and validation set error are evaluated at each iteration of the training and not at the end of the epoch, right? You can do both. Usually they are at each iteration, correct? But you can perform that at each epoch. For early stopping, is better to wait the epoch. So you are more resilient to noise given by the mini batches. But selecting the validation set among the values in the blue part, is there a reuse of the same sample? First a training set and then as a validation set? No, because you split them. You split those parts. you split those sets. I will come back to this later. Does it always exist a point in which the derivative change sign and start increasing? For yes, the problem is that it is gradient descent is very noisy. So basically, what happens is that it is a very noise curve, the validation set. When using the K4 cross validation, the training set and validation set sums up. Okay, let's do this way. Let's take a break and let's come back in 10 minutes at 6:15, and I will show it again on paper because it seems that there are too many questions and I want to make them clear, and I will do it on paper. So I will stop here the recording. So I will stop it. Unfortunately, I need to stop because what happened? Okay, should be stopped. I hope so, but it doesn't seem to stop the recording. I stop the sharing. It seems the system is stuck. Oh, sorry. Oh, here we go. No, instead of stop, I will put it in pause and I will resume it later on. Okay. Let's take 10 minutes of break. In the meanwhile, I try to stop some paperwork and we'll come back to this right after the break. See you at 6:15. Okay, you should be able to hear me. Can you hear me now? Okay, I see someone has heard the microphone. Was not mine. I know whose microphone was, but was not mine. Ensure. So let me try this. Unfortunately, I don't know how to mute. Suddenly, now it's muted. I couldn't do it. Okay, uh, let me start. Let me resume. The uh, microphone is cracking. I don't know what to do. I don't know what it is. I think that the sharing of the camera and the microphone is the issue. Can you hear my voice now? Can you hear my voice? I don't see any reaction on the. Oh yes. Okay. Thank you. Let's try to uh, clarify a couple of steps. You should be able to see a piece of paper. So let's try to summarize with the picture the concept, which is this. So you will have usually a data set in the form of a table, which is this. Okay, and this is the data set. So one thing that you should do is to first split the data in training and test. So this is training and test. Okay. Now, this you could do by using also what is called k-fold cross-validation. But this means that you repeat this procedure k times. So test, training. Now, the test should not be touched until the end. So let's write it red. Don't touch the test. Now you have your training data, which I report here. This should have the same size of this. And you can decide to further split the training data in train and validation. With this data, you do, let's say, model training. With this data, you do model model selection, or let's call it model selection. With this, you do model evaluation or assessment, or sometimes it's called, unfortunately, validation. This ambiguity comes from the fact that not in all systems you need to, not in all machine learning system, you need to perform this first split. I mean, this is, but let's assume that these are the sets. One is, let's call it final, very final model evaluation assessment. Let's be very official. This is done by the development team. This is done by the production team or another team. Production or pre-production. Production. Okay. In your, let's say, toy examples with the, let's say, small projects that you will do for the competition, you will do both activities, or you might decide that we do this and you do this, but in general we will give you the test and the train. Then it will be up to you to basically further split the training and the validation to perform this activity. So this is the basic idea. What does it mean, model training? In the neural network terms, this is backpropagation. What does it mean, model selection? Well, it can have different meanings. For instance, it could be early stopping. So when we talk about model evaluation, we talk about this idea that the model should not be tested on the training, but on a test. So you have training and test. When we talk about, let's say, model selection, we usually talk about the fact that you train on some data and you use some other data to select which was the best configuration of the model. So you see that you have a sort of two-level approach. I mean, test on different data with respect to the training, validate, which means do decision about the training, which should be disjoint from the final model assessment. Why? Because you could take some selection which basically might be too optimistic, because when you select, you have seen the data. And because you have selected, in a sense, you have overfitted on the validation data. So that's why this test set should always exist. In the early stopping, we talk about this training data and validation data. So if I should report the plot of early stopping, what I expect is that your training data will be like this, and then go with the number of epoch, the errors will go to 0. So this is the expected error for training. Then I have the validation, which will have a minimum. This is a more realistic plot of the validation. So I will stop here. Now, what will be my test data? Well, my test data could be some. No, this is the wrong color. Let me take another color. Could be something like this. Oh. Usually, the test data, so these are test data. Usually, the test data have a behavior which is more similar to the validation data than to the training data. As you see here, in this case, the performance on the test data is worse than the validation data. You should expect it. And if you see here, if you would have waited a little bit more, the performance on the test would have been better. But since you will never see this data, then you will never know that you could have waited a little bit more to stop. So basically, you do backpropagation, you stop the model, you take this model here, which is a neural network trained for K epochs, you send them to the production, you will get paid that much, which is for the test error. If you could have known that training a little bit more would have paid something more, you would have gained much money. But you will never have a way in that shouldn't be that you assess this number. Okay, lots of questions. Training set, lessons and personal exercises, assignment, final exam. Yes, more or less is the correct similarity. In this schema, where do I compare the various models that differs by the shape and numbers of neurons? I will come to this in a minute. So we choose models where the performance of training data is better than validation. No, we choose the model where you get the best validation. The model you select is the validation, because this is validation, this is train, and this is test. If you wanted to say test, you understand why this is complex. This is with the single holdout, it's not with the k-fold cross-validation. So, validation, train, test. Now, what if
Professor, can I speak?
we put this into a k-fold cross-validation setting? This makes much more complex. So wait a minute, because I want this to be totally clear, because it's a very key perspective. Just a second. I would, yes, yes, go on,
Yeah, Professor, to interrupt
go
you.
on.
Professor, in the graph that you right now, you said that
I
we
don't
do
hear you
back
anymore.
Yeah, am I audible now? Am I,
Okay.
am I audible, Professor? Hello?
Yes, but it's very noisy.
I'm sorry. Professor, you
Yes,
said
now
that
you are.
yeah, Professor, you said that we do a back propagation. If I'm
Yes,
referring to the graph that
you
you
hear.
said, we did a back propagation, and we stop at that point where the curve for the test is higher than that one of the validation. So why are you stopping at that point? Because the performance of the test is better than the validation, right?
Yes, but you will never, ever, ever see the test. You are the developer. You don't have access to the test. You are the
Okay.
developer. That's the key point of all this story.
Okay, but then on what basis
And
shall
to
I
have a
choose the
correct
model?
evaluation as a developer, you should never take decision on the test set. That's the key point. So you are the developers. Then, sorry. So I think that the problem is with my voice and my. So okay, let's do this. Wait a second. Okay, someone here. Well, okay. I don't hear any more Sardashan.
Sorry, Professor. Like I thought, like you
Uh,
are not able to hear me out.
so there is a very good question. So let me. So I hope you hear me now. So there is a very question at this point. If I train on, and if I train and my validation set, I can hear you now. Now I can. I think that there is a big lag in the connection. So my suggestion is that you write question in the chat, and I will answer the question in the chat. I think that will simplify the communication. My way is if you can hear me. So please answer if you can hear me. There is a lot of latency. So let's wait try action and so let's stop. Sorry, let me take. Okay, so there's surely a problem with the connection. Okay, let me stop sharing this. Let me stop with the camera. I think that one of the problem is the use of the camera. Okay. I hope my voice is better now. Can you hear me, Val? Is it good, my voice now? I don't hear anyone. Okay, hope everyone hear me. Okay, so okay, good. Thank you very much. So let me. Okay, good. So let me go back to the slides. Unfortunately, let me go back to the slide. To do this, I need to become again the presenter. Sorry. So give me a second. Ah, why? Let me go back. Okay, I need to become again the presenter. Okay. Okay, now should be able to share the slide. Now keep in mind the picture that I was drawing on the paper. Can you see the slides now? Can you see the slides? Okay. Okay, thank you very much. So, if you look at the slides, the green curve is what you get from backpropagation. The red curve is what you get when you test the model at that backpropagation epoch on the validation step. You stop, as you see in the picture, when the validation set is the minimum. I hope this clarifies. Oh, okay, I hope so. Oh, I see in the chat that someone already described this. Okay, so let me go back in the chat to see if there are other questions. So, first of all, very please. Okay, so we choose the model with the validation set, validation set error, which is the minimum. Now, I hope that there is no more latency. The question is, could you clarify what do we change in the artificial neural network with the different types of tests? So far, nothing. So training set is equal to backpropagation. No, training set is the test on which you perform backpropagation. So you feed the weights. The validation is a set that you use to say how good is the current validation. And after the validation, you send to someone else the model, and this is the final good, the final, let's say, value of your model, the final performance of your model. So the question is, if I train my data and my validation error is bad, we can train again on the same data but change the validation set? No, you have to change the model. So the point is this, if you train on a training set and you get, let's say, an error, and you test and you validate on the validation data, and there is a bad result, this is a message of the fact that there is overfitting, for instance, in your model. But don't stop it with k-fault validation. You are getting too much confused. I will come back later on k-fault cross validation, but now forget about k, because you are messing a few things. So I want this picture to be crystal clear. So that's the more important. Then variation, k-fold. I mean, these are fancy things which in practice you can do, but makes the process very, very complex. So right now, I need this picture to be crystal clear. So are there any other doubts on this picture and on the picture that I draw on paper? Okay, I don't see any other questions, so I assume that things are now. Let's go on this idea that the validation set are basically giving you an idea, an estimation error. In this picture, decided to stop when the model, let's say, starts overfitting. In general, you can apply the very same idea of training, validation, and testing also for other aspects of the training. If you remember, we talked about the idea of hyperparameters. So those hyperparameters are parameters which enter in the training process. So, for instance, you have to decide when to stop the training. This is an hyperparameter. So the epoch at which you stop the training is a hyperparameter. Another hyperparameter could be the number of hidden neurons. Another hyperparameter could be the number of layers in a neural network. So basically, we have to think at three levels of model evaluation. And these three levels are the levels of, for instance, parameter tuning, levels, let's say, hyperparameters. So when we adapt the model, we are at the parameter level. So for instance, we learn the weights for a neural network. At hyperparameter, for instance, is where we choose the number of layers or the number of keyframes called hyperparameter layer. There is another level. So when I say parameter level is backpropagation, are the weights. The parameters are weights, and you are adapting them going down the hyperparameter level is, for instance, very bad audio. Okay, so let me try to log out, relog, because I think in this condition. So let me try to stop and relog again. I will be back in a minute. Can you hear me now? Is it any better? Oh, okay. Sorry for that. Today is complex, as you see. I would like to. Now I have to figure out how to become a presenter. Yes. Okay. Just give me 1 minute, and I will fix also this. Okay. Can you hear me now? Okay, good. Thank you. I hope this time the audio goes better. I'm trying to. I will resume uh, the video. unfortunately, and I will try also to make myself speaker, but this is I don't know how to. Just a second, I cannot share slide anymore. Okay. Let's see if I. It seems I cannot share the slides. I don't know why. Oh, now I can. Okay, thank you. Okay. 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 Can you see the slides now? Okay, thank you. So, okay. So, the idea of training and validation is that you have two sets for training a neural network and for testing and for validating the neural network. And this difference is an idea of the gap between your training set and test set. So this idea of this gap is telling you whether your training is going well or is going bad. And it is telling you how good is your model. So, for instance, let's assume we have a neural network with one hidden layer, and this network has this plot of training set error and validation set error. Your network will, just a second, I don't know if yes, I'm already recording, so just double checking. So this network will have at when you stop to train it, validation set error, which is this point, which can be considered the generalization error of a network with J neurons in the first hidden layer. So and so you can imagine that if you have one neuron in the hidden layer, you will have your network with this generalization error, which is this error. Then you try to add one neuron, and you do exactly the same. You train on the training set error, you use the validation test error to stop, you will get a second error here. Then you do it again, you add another error, another few neurons, and you get this error. It means that you train another network. This time you put more neurons in the hidden layer. You do the training of the network. You do the validation set stop, the early stop. You get a number, and this is here. If you repeat this multiple times, you will get more or less a curve like this. What does this curve say? This curve says that if you increase the complexity, your generalization error, as measured by the validation set error, will decrease. Because it decreases, it means that you should increase the number of neurons. So if you increase the number of neurons, this goes down, 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 until this point. What happens after this point? After this point, every neurons you add will try to overfit, and early stopping will prevent it. So what we are doing at this point is, at the same time, preventing overfitting, because we are reducing overfitting via early stopping. And we are performing model selection because we are selecting the model complexity here. We are testing different models for the, let's say, for selecting it. It is a mistake that the ninth neuron's error is higher than the fifth neuron one. No, it might happen. It might happen because every time you restart the network from a different initial point. Plus, you are doing batch gradient descent. So these curves are noisy. You should expect these curves a little bit noisy. The fact that the 9 is a little bit higher is to show that it might happen that you have a slight increase uh, in the curve. But on average, this is too exaggerated, but on average, this is what you see. Oh, great question. But aren't we sort of overfitting on the validation set by using it over and over? Yes. And that is why at the very end, the real quality of the model will be given by the test set. The test set is used at the very end and solely at the very end to say how good is a model. Why? Because the validation set is a sort of proxy of the generalization error. We keep using it again and again. So, in a sense, we will end up to be too optimistic in evaluating our model. And because of this, the final statement on the accuracy of the model will be given by the test error set. Is the generalization error the same of validation error? Well, yes and no, in the sense, if we go back to the previous slide, I say that the validation error is a sort of estimate of the generalization error. What is the generalization error? The generalization error is the difference between what you expect from your training and what you will get on a different data set. So the validation can be assumed to be an online estimate of the generalization error. When you stop is your estimate of the generalization error, is your estimate on the performance of the model on data which were not used for training. As your colleague pointed out, it is not totally true that were not used for training, because in a sense, they were used to select the model. So your model selection is biased or is fitted on the specific validation set. Because of this, if you want to have a totally unbiased estimate of what will be the performance of your model, you need another set, which is the test set. Questions? Is everything clear? Okay, if I train my data and my validation error is bad, we can train again on the same data but change the validation set. The problem is you cannot change your validation set. Because your validation set is the data you have set apart from the training. If we get the picture, what we get is that if you change the validation, you have to change the training, because the validation is an extraction from the training. So you cannot easily change the validation set. If you change the validation set, you also change the training set, because you train on a different data set. So again, this is the reset. Changing the validation set is an ideal situation. Well, the ideal situation is to have an infinite number of data. That's the ideal situation. If training set, validation set, and test set are huge, there is no problem. When they are small, you have to be cautious in what you do, because you can sort of overfit it. So a question, I don't understand where those points come from. Let me go back. As I said here, this first point here is this is the validation error when you finish the training with a neuron, with the network with one neuron. Then you restart, you retrain another network with the second network with two neurons, and you will have another point, which is the point where you end the training. Then you do another network with 5 neurons. And then you do another network with 9 neurons. These points are the validation set errors when you stop. That's where they come from. Doing early stop is like fitting poorly the training set on purpose instead of changing the model we are fitting. Yes, in a sense it's true. The way we should change it is simplifying it, because it is fitting poorly. It is not just fitting poorly, but assuming that you first fit the real data and then you fit the noise, it means that you stop with the phenomenon and you keep away the noise. So we have to recompute the validation set error and training set error for every network. Yes, correct. You have for every network train this. The real difficult part in training a model, especially a neural network, is this one. I mean, setting up one network which works with the data set is easy. The point is when you want to find the right network or improve your network. You have to set up a methodology. This methodology expect you to set up a validation set and to do many experiments with different data points on the validation set error. Train on the train, check the validation, and then you always use the configuration, let's call it this way, the hyperparameter set, which gives you the best validation error. When I validate the model on the validation set, I give the network the data and inputs, but not the outputs. No. No, wait a minute. When I validate, okay, sorry. When I validate the model on the validation set, I give the network the data and input, correct, but not the output that I have. So the network will not backpropagate and modify its way, correct. And the same happens on the test set, correct. So in the validation set, you don't train, you don't perform backpropagation, correct. So backpropagation is only performed at training time. Okay. How about if you want to decide on the number of hidden layer after deciding the number of neurons? Well, wait a minute. You cannot decide the number of layers after the number of neurons. So basically, the point is that the number of configuration is quite big. You have to test them all. So you can say one layer with one neuron, 2 layers with 1 neuron, 1 layer with 2 neurons, 2 layers with 2 neurons. You try all the configurations that you want, and for each of them you will have a point on this graph. Actually, it would be a set of configuration of a grid of possible configuration. The selection on this grid of the best model is called grid search. Is there a rule that says the more the neurons, the less the error? Yes, is the rule that was in the first slide of today. The more neuron you put, the less could be the error on the training set. But we know that we don't care of the error on the training set. We care about the error on the validation set. And these points are on the validation set. It means that if you trace the error at the increase of the complexity, this will go to 0. But this error is not something that we want. We want to predict the error on data that we have not seen. And this is obtained through validation. But then how can we overfit on validation set? We don't learn on it. The term overfitting that was introduced by your colleague is the fact that, let's go back. What is overfitting? Overfitting means to have an optimistic estimate of the error with respect to what you will get on the real practice. That's overfitting. So, overfitting on the validation set means that all this procedure is optimized for the validation set. It might happen that when you go on production, you will get results which are less good. I mean, this is true. Why? Because all your choices are based on the validation set. The problem is that if you base them on the training, they would be awful, because you can always send to 0 the training set error. Just increase the number of parameters. At the end is correct. Sorry. At the end is correct to choose as hyperparameters one of the first of the flattened zone. Yes, it is the Occam's razor. So you should select, let's say, the one with the simplest model with the best validation set error. Correct. Could we use the number of epochs as another hyperparameter without early stopping? I am not sure I'm getting the advantage of early stopping with respect to traditional model selection, where the number of epochs is another hyperparameter. So let's assume you do this. Let's make it as a hyperparameter. Basically, you are doing early stopping. If you say, okay, let's see what happens when I train with 1 epoch. You train with 1 epoch, you test on a validation set. Let's see when you do 3 epoch, 4 epoch, 5 epochs. The plot on the left is exactly treating the number of epochs as an hyperparameter, and you stop the sooner here. If you don't do it, what you will do? You will train until the end. No way. You will, by definition, select a wrong test error. So basically, you have a stratified approach in which you first limit the validation set error with the early stopping, and then you select the other parameters without the early stopping. Is necessarily to have early stopping always? Can we train without early stopping? Yes, we can, but we have to do something not to have this huge gap at the end. Early stopping is just one of the possible techniques to prevent overfitting. Is the easiest, is one of the most effective, is the one that reduces the training time the most. So it is something that I always suggest to have early stopping. I don't get how the validation training is related to the neural network and backpropagation. Training means that you're doing backpropagation. Validation is that you are using the network with the weights that you have learned at that epoch. Training is equivalent to say, I am applying the backpropagation formula to my network. Okay, so on training set, apart from gradient descent iteration k and b number of neurons, which other parameter reduce the error? Okay, during training, the number of neurons, the number of layers, and the complexity of the model in general reduce the error. These are the two elements that enter in the training error. Then we can add other elements that will be described at this point in a different lecture, so that we reduce the gap between the training and the validation set error. But right now, the only two elements that you have to reduce the error are the number of iteration and the number of neurons. In some conditions, also the learning rate, so the choice of a proper learning rate is obtaining a lower error or a bigger error. So you can have the learning rate as another hyperparameter. So that's another possible choice. So we have to train each model twice, one for finding at which epoch to perform early stopping, no. And one for training again the network. No, you don't do that. I mean, while you train, you test. You train, you test. At that point, you stop, the model is already trained. So you don't have to train it twice. Why to train it twice? Is there a best way to alternate training at parameters, hyperparameters level? The two seems to depend on each other. Yes, so the hyperparameter is the higher level. It is the selection of your model. To select your model, you have to train it. So basically, training is the basic block. And it is the block that you do when you have decided how many neurons, how many layers your network has, what is the error function, all the details. You train. The problem is that if you train without considering overfitting, you will overfit. And my suggestion, one of the suggestions to reduce overfitting, is to use early stopping. Then this is the basic block, training with early stopping or training with some overfitting limitation. What you could do is to put this basic element in a more complex procedure, which will be used to select the model. Okay. Okay, I think that I hope that there are no other doubts and questions. Let me go back 1 second. So the idea is that we should always choose the model with the best validation error. It exists another level of model selection where learning happens is called meta-learning, but we will not discuss within this course about meta-learning. So in this course, we will talk about learning, the parameters, and we call the weights of a neural network parameters, and we will discuss about model selection or hyperparameter selection or hyperparameter tuning, which is the number of neurons, the number of layers, the activation function, and some other. Okay. Is early stopping the only way? Let me go back to limit overfitting. So is this the only way of limiting overfitting? The answer is no. There are other techniques, and I would like to discuss at least two other techniques to limit overfitting. The first one is weight decay, and the other one is dropout. Why these two techniques? Because these two are these three techniques, which are early stopping, weight decay, and dropout, are the three most used techniques to train neural networks and to prevent overfitting in neural networks. But obviously, I will stop here today because, I mean, we are already longer than expected due to the technical issues that I had also today and to the complexity of the topic. I will publish the slide. So slides are already published. I will add a couple of slides, and one of the slides that I will make, which I hope it will happen, will help to understand the whole picture, is the one that I draw on paper together with you. In past years, it was more clear. I don't know whether the complexity comes from the fact that some of you did not ever took a machine learning class, or the fact that unfortunately there is this clash of terminology on what is model validation, what is the validation set, what is k-fold cross validation. The validation set in the neural network terminology is this specific set, which is used for early stopping or for hyperparameter tuning. And it's part of a more complex procedure of model selection, which exists for any machine learning algorithm, not just for neural network, but for neural network, since they are very complex model, this procedure can become very, very, very complex. Okay, any final question? Okay, I don't see any other question. If so, I would like to stop the recording. Okay, today the recording will be very strange, unfortunately, due to the complexity of the setup. I'm very sorry for that. I think that this remote teaching has still some problems with respect to the in-present teaching, but we are still in the condition that we cannot yet go back to class together. So my suggestion is to stop here. We have classes next week. In particular, you have a lecture with Francesco on Wednesday, if I'm right, where he will start exercising with training neural networks, and in particular, he will discuss also how to implement with Keras the early stopping procedure. So basically, next week, Francesco will implement the training of a simple feed-forward neural network, and he will show you how to implement the overfitting prevention via early stopping. So question, Wednesday will be in presence or online? If there is no last minute issue, it will be in presence as planned according to the schedule. So just a second, Professor, will we have theory class? Sorry, can you rewrite the sentence? I didn't get it clearly. So next, sorry. Will we have a theory class next week? Right now is not in the schedule. The reason was that it was not planned, that lecture. There is a free spot on Thursday, which is one of the which is the a free spot. To be honest, we are. Don't worry, I know perfectly the problem of keyboard with errors. There is a problem. Sorry, there is a hole in the schedule. Since we are slightly late, I would like to do theory lectures on next week on Thursday, so to finish this block of slides. The reason why I want to finish this block of slides, I'll tell you very clearly. I don't know what is going to be the health situation in Italy in the next months. So I would like to do the biggest block of lectures the earliest possible, so to allow you to acquire all the material as early as possible. So because of this, I think we might decide to add the lectures next Thursday so that we be able to finish the program. I think that you will not complain if we can finish the program earlier than expected. It will be only useful for you to prepare for the exam and so on. So thank you for your question. I will double check with Francesco and Giacomo, but we might add, we might fill the spot that was intentionally left in the schedule for the 15th so that we get perfectly in track with the program. So expect an email from me in case this happens. As usual, the lecture will be recorded and it will be posted on the website, but given the highly interactive nature of today's lecture, I suggest you to attend in person and ask questions as you did. Any other question? No? Okay, hope so, because we are left in a few participants at this point. I would like to stop here, and we will meet again with Francesco in presence on Wednesday and with me on Thursday remotely, but wait for my communication. Bye bye. Thank you for your questions and for stimulating a very proactive lectures. During the weekend, I will update the slides with the validation schema that I drew for you. Bye bye. Thank you.